Alrighty. Welcome, everybody. Thank you for joining us today. Welcome to the Student Design Hub Speaker Series, Design Leaders in Tech. And in this session, we invite local speakers from the Newfoundland Labrador Tech Startup community to come and discuss how they approach product development. So before we get started, just a few quick housekeeping items. You may notice that you can't see the other attendees in the WebEx. You're not alone out there. WebEx events disables the chat function sometimes, but we have it open on this one. So feel free to type your questions either in the chat section or the Q&A. It'd be best if you did put it through the Q&A section, though. That way we can see them and we can kind of direct them to myself or Greg if you're having a technical issue or what have you. So if you have any questions throughout the presentation, ping us in the chat or the Q&A section. And if you would like to ask your question in person, just write down, I would like to be seen, or I would like to ask my question. And then that way we can bring you out of the audience and you can ask Greg your question directly. So if you're having any technical difficulties at all, feel free to shoot me a message. And without any further delay, I'm going to hand it off to Greg Walsh, the mechanical team lead at Kraken Robotic Systems. So Greg, you might be muted there.
Cal, can you hear me now?
Yes, sir. We can hear you now.
Weird. Okay, I didn't have an unmute button here, so I just want to check and just to make sure that you can see the same screen that I can, or I guess the presentation screen.
Yes, sir. We got your title slide up there now.
Okay, great. So I guess just to fill out a little bit more of what Kyle just mentioned, I'm Greg Walsh. I think I see a couple of familiar names there in the attendees. I'm the team lead at Kraken Robotics for mechanical, and I'm just coming here today to give you a little talk about the design process, not necessarily the Kraken design process, but more because it changes from company to company, but just the mechanical design process in general as I've experienced it over a course of a couple of different positions. So I'm an engineering graduate, so graduated from the same program, I guess a little bit earlier than most of you attending did. And I've worked with local tech and marine tech companies over the course of my career. So most recently Kraken, prior to that it would have been OneMed 3D in medical, and then Heddle Marine Services, which you might now know as Heddle Shipyards, and before that would be Subsea Imaging. Just to cover off what we're going to be talking about today, I'm going to go over what the design cycle is, then walk through a basic design cycle. And after that, I'll highlight some challenges often experienced early in designs, how clients interact with the design process, and some tips to keep in mind when you're working in design. So just to start off, a few days ago, I picked up a book while out running some errands, and once I had a chance to really get into the book, I was surprised because it wasn't an engineering book or a text, but I was surprised at the insights it provided into how the design cycle can be applied to everyday life and everyday problems. It's a great book. I highly recommend anyone out there that's looking for a good read, go out and buy it, but if you don't, we're probably going to be able to cover most of the main points here today. So in this book, and it's a kid book for very young kids, obviously, Splat the cat has a problem. His first job is delivering newspapers, and he can't get out of bed early enough in the morning. So Kitten, the consulting engineer, submits a proposal to build a new, more effective alarm. And this is what I thought was pretty neat. Again, I said like it's a book for very young kids, but it's still laying out that design cycle, maybe something in simple form that your kids will take away from it. So as I've got note annotated to the side here, a really basic design cycle is you make a plan, you make a design, then you prototype it, you test that prototype, you revise the design, you test again, and you go through the iterations of that design cycle. So here we go, perhaps a more formal display of the design cycle. And really something to highlight here is that everywhere we'll use a slightly different design cycle. Stages will be called different things. There might be more formal reviews added in here, but all of these basic steps remain. So again, we'll start with identifying the problem and constraints. So this is really, what are you trying to solve here? You research the problem, brainstorm some solutions, come up with some possible solutions to the problem. You plan or select a problem or solution to the problem, and then you prototype that solution. And sometimes you select more than one solution, prototype it, see how they perform comparatively. Then you test and evaluate that solution or prototype. And then depending on the performance in your testing, you revise it, improve. And really that's the start of the cycle again, the revise and improve, because what you're asking yourself in revise and improve is, what is my problem with this prototype? Or identifying the problem with the prototype, or the remaining problem with the prototype. So we'll just walk through each of those individual steps in a little more detail now. Again, identify the problem, set constraints. What you're determining is what you're actually solving. One of the key things to remember here is that you should really limit the scope of the problem to something that's achievable, and make sure you don't get scope creep and end up never completing the problem or never solving it. So that means sometimes identifying what you're actually not going to solve. I know one thing that was my favorite line probably in school was basically, this is not part of the scope of this solution. And really you use that even more and more in the workplace, because you want to make it clear to whoever's getting this design that these things aren't covered and you're solving a very specific problem. It's not all encompassing, you're solving a very specific problem, and you should state that problem clearly. You also need to set constraints, or at least find out about the constraints. Constraints might be engineering constraints, but often they're also time constraints and cost constraints, schedule constraints. You want to state your primary assumptions. So this would be anything you're assuming in order to have the problem stated in a context that is solvable. And you also want to document your scope and specification. So everything above, including what you're solving, what you're not solving, the time constraints, the cost constraints, any other constraints, your primary assumptions, you want to document in scope. So you want to make sure that this is down in writing somewhere. The reason for that we'll probably talk about in a couple of slides. After you have your problem stated and stated in a cohesive manner, then you can move into researching the problem. Now this is probably a little bit different than you would in school or academically. In commercial engineering, you're trying to probably, a lot of the time, not come up with anything that's too new or exciting. So your problem that you're trying to solve has most likely been solved before. Something very similar to it has been solved before. And even in very unique solutions, building blocks of those very unique solutions may be actually standard solutions, things that have been solved before, things that have been researched, things that have been well documented. You don't want to reinvent the wheel if you can avoid it. And the reason for that is time and cost. Commercially, obviously, engineering is a revenue driving function, I guess you could say. So if you can reduce time, reduce cost, increase the simplicity of a solution, then it is more profitable. And often more effective, because it's well tested. You're just making a small modification to a well tested design. So that could also be an increase in safety as well. This stage is also somewhere where you'd want to research the best practices and applicable codes or standard. So if just talking about the marine industry, we've got DNVGL, or if you want to move into mechanical a little bit more, you have ASME and ANSI, all have standards and codes that apply to certain design situations. So sometimes you might have to get a design certified. Other times it might just be you're using the standard as a best practice for your design. And again, you want to document this, because once you dig into the design, you want a reference to keep going back to make sure you don't forget anything, or you don't mix up numbers or codes or any of the details that you don't deal with on a daily basis during your design, but you can quickly reference them. After you've researched the design, you want to brainstorm some solutions. So I always recommend that you work backwards from a problem. What is the minimum or most efficient solution to meet the goal? You really should try to avoid getting caught in the trap of having a solution looking for a problem. And just as an example of that, if I said to you, I came in and said to the classroom that you're sitting in, not sitting in, I can't remember, but in front of a class when there was such a thing, and said, I've got a camera here and I want to take a photo of the class, but my hands are a little shaky. I want to be able to adjust the angle that I'm taking the photo at. Maybe I want to activate it remotely, and I want it to be really steady and probably at a certain height. I said, give me some solutions. My budget is $5,000. I'd probably have a few people who would suggest a tripod. But if you look at my problem, I just want the camera to be held steady and to be able to change the angle it's rotated at. Why couldn't we put a box on a desk and lay the camera down and press the button and then walk away on the timer? That would meet the minimum criteria that I stated I wanted solved, and it's also free instead of $5,000. So I think working backwards from the problem, really making sure you've identified the actual problem you're trying to solve and not starting with a predetermined solution in your mind and then fitting the description of the problem to work with that predetermined solution is key in this. And that is why documenting the scope is important. You can go back to the scope and you can look and see, hey, we said we're solving this problem only. This meets that minimum goal. And the reason for meeting a minimum goal is, sure, your design can solve more than that, but meeting the minimum goal solves the problem. And that's probably your most cost-effective and efficient way, time-effective as well, to come up with a solution to the problem. I'd often throw out 3D printing as a good solution. That's often used for the wrong problems. So, 3D printing is very trendy. Everybody wants to use it for everything, but it's not really good at a lot of stuff. And some people just want to hammer 3D printing into every situation and every problem as the preferred solution. But you really need to step back from that and look at it and say, 3D printing actually isn't super cost effective in a lot of situations. It definitely doesn't provide the same type or quality of parts in certain situations. And then in other situations, it's actually the preferred solution. So it does excel, but you have to identify the proper solutions or proper problems to use it for. So again, work backward from the problem. Don't start with something and say, how can I take this and make it the problem change, the problem scope change, so I can use this solution that I want to use over here. And then sometimes commercially, the preferred solution is the most available one due to non-design constraints. So, there are times commercially when you're going to have to change that scope of problem that you're solving, and maybe you are getting something that isn't the most efficient, is super over the top, solves your problem plus 100,000 others, but the reason you're using it is because there's a time constraint. You need to have it delivered by next week, and hey, this part that does way more than it's supposed to be is available from McMaster in 2 days, so you're going to take that one. Cost, obviously, maybe not play into that. So again, and just to highlight what I'm saying there, it kind of looks like I'm contradicting myself, but really engineering in the commercial environment is all about making the right decisions. It's about experience and choosing the things. It's judgment calls constantly. So sometimes your judgment is, you know what, I'm going to have you use a design or a solution that's not the most effective. But when you have the ability to, what I said before, start from the problem, work back from there. And that would be sometimes you're going to have to fit a square solution in a round hole and just make a solution that's available or that you have work. Selecting a solution. I think probably what you would be familiar with is creating a matrix and then having weighted criteria and objectively choosing the optimal solution. And you weight the criteria so the solution you would like would be the one that's actually chosen. Because it's really hard to be impartial in the design selection, especially when you have a horse in the race. So it's good in practice to review designs as a group and think over before selection. Give justification for individual selections. So once you make the selection, or once you have a group of ideas, everybody on the team sit down, review it, you discuss the ideas, give some time away so people can think over it individually, and then have them fill out the selection form. You should probably also create the selection form as a group so you can agree on what is the most important factor or feature of your design. And then once everybody does make their selection, give a reason for your weighting. So if I score this propeller as a 1 on the efficiency scale, being the worst out of 10, I should say why I'm doing that. And it's not just because I don't like the design. I actually have a reason for it, and that will also make the person think about, why am I doing this? Why am I rating it this? And again, this can actually be decided other ways. Selecting your design can be decided in other ways. And the matrix, I would say, is probably less common depending on the size of the team and the size of the project. You can also have a group or majority consensus within a group. Often it's hard to have groups consensus, so maybe a majority would be the best to go there. Or you could have decisions made by a senior or more experienced team member. And the design could also be chosen by the client. You could present the client with a bunch of designs and see which ones you're going to progress from there. So again, there's no one and only way to do this, but there are a couple. Prototyping. So prototypes can take various forms: physical, like actual test pieces; digital, CAD models for FEA, or maybe a motion analysis; and even paper, hand calculations, or a very simple, basic first principles analysis of your actual solution that you're creating or designing. Also, a prototype can be a simplified version, like I just said, on paper of the solution. So even prototypes could be complex, and maybe you don't have the time or budget in order to develop a fully complex prototype, or maybe it's just that a full prototype would be close to impossible to solve or to test. So you might have to simplify it. And maybe it's because you can only measure things in certain ways, or you only have certain equipment available. Maybe it's because you have to fixture your prototype to something that you have available, or in a certain way to test it. So you might have to modify your design, your prototype design, to actually test the prototype. And really, skill and experience there help determine the proper assumptions and constraints to use in a simplified model. Why do we prototype? Well, again, it's faster and cheaper than testing production designs a lot of the time. And just as a highlight here, this is actually an area where additive manufacturing, 3D printing, is usually a fairly good solution, because it's commonly a one-off part and you need it fast, so the turnaround time is quite quick, and that makes 3D printing cost effective as well. One other thing to highlight here is that your prototype testing may not actually be a complete prototype. It actually might be the prototype solution broken up into testable units. So you actually test one part of the prototype at a time instead of the whole assembly or the whole unit. And that kind of leads into the testing. One thing you want to do when you're testing is make sure you determine the testing criteria beforehand. So the criteria and outcomes should really be based on your initial scoping document, the thing we talked about first. You should go there and say, again, hey, what are the minimum problem, or what's the minimum problem that I'm trying to solve here, the minimum solution to the problem I'm trying to solve, and then base your test and your criteria of your test around that. Criteria would probably also be, copying a lot of or putting in those modified conditions and assumptions that you had in your initial scoping document, and then the follow-up research. And from that, now you've got your test set up, your testing plan. You want to determine the acceptable outcomes beforehand. So what's the target outcome? And then how are you going to rank it as being achieved or not achieved? Then you conduct the tests. Make sure you document this as well. The test data, I know for a fact I've run some, and I wish I had been better about documenting, and have to go back and kind of dig through stuff to try and find the answer for something that I thought about later. So make sure you do document your tests and your record your data results well, and keep them handy. Then you want to evaluate the outcome, and evaluating the outcome should be based on the outcome or acceptability of outcomes that you determined in the initial stage of testing and evaluation. So you don't want to just test it and say, yeah, that's okay. You want a little bit more objective criteria. So make sure it's related to your scoping document. Make sure it's document or your outcomes, acceptable outcomes, and how you're going to measure them are documented before you test. And then after you test, take your data and look at it and say, does it meet the outcomes or not? And just as a highlight here, I know talking a little bit about how clients affect or interact with designs, clients are often involved in testing. Sometimes the client might be testing the prototype for you. That's happened for me in a couple of situations. And sometimes even they're gathering the data for you and giving it back for your analysis. So just something to think about there. Then after testing, you kind of roll back into the design cycle again. And this is where you restart the cycle, but with the prototype. So you look at your prototype, you look at your test data, you look at your conclusions from your test data, and you say, do my initial documents need updating? So does the problem, assumption, scope, or constraints need to be changed with what we know now about how the prototype works? You know, you might hit it right the first time and the prototype solves your problem completely, and then your answer there would be no, and we can actually move this into production. But usually in the context of the prototype, you're still going to have a problem, how it can be improved and what can be improved. And the clients often as well, like I said, they might be usually involved in testing or often involved in testing. They might actually put some more requirements in there that you didn't see at the beginning. So after testing something, you might say, hey, you know what? We never thought about it before, but we want this solution to do an additional thing. So make sure you document those changes to the initial scope as well. Just to make sure, again, when you're starting the second design cycle, you do have that reference. And if you ever go back, you can say, hey, you know what? Originally we set out to solve this problem. Now we're solving this problem plus, and here's the reason why the cost of your contract increased. So then you arrive at a solution. A key thing to keep in mind is that the design cycle has to stop somewhere. And you need to kind of determine beforehand where that's going to stop. I'd suggest it stops on meeting the minimum criteria usually. This point is often difficult to determine, especially for junior engineers, because you're coming out of school, you just want to keep refining designs until they're perfect. They're the best design ever. They're amazing, and they solve all of the problems all of the time. That's not real design. Real design is a specific solution to a specific problem. And again, one of the things that helps with that is that scope in the beginning. Make sure you scope out your problem well and you state when it is going to be solved. So other than meeting the minimum solution requirement, there might be other constraints as well. So it might end on a time constraint and it might end on a cost constraint. Two things that aren't, I'll call them like non-engineering constraints, but very real in the commercial environment. So you might have a deadline to deliver this by, you might have a cost to deliver it under, and then that's the solution that you end up using or something very close to it. Maybe not the one that you would have if you went through another 5 design cycles. And this is just another couple of things to keep in mind when you're designing, going through the design cycle. And again, none of this is all encompassing. It's just a couple of tidbits of information to kind of get you a little bit more thinking about commercial design versus what you're doing now in school, your academic design. Early challenges in design. I've said this a bunch of times here, but correctly identifying the problem. Again, this sets you up for failure or success all the way through your design and your testing. If you identify the problem correctly, it makes life a lot easier because then you are finding the right solution, number one. But also you're going to have the right scope and you're going to make sure that you end your project or your design at the appropriate point. One thing here is that problem is often not what it first seems. So sometimes the client will say something like, I want XYZ camera system. But really, you know, it's a very advanced, full color, sensitive camera with 4K video and LEDs, and it's pressure rated to 7,000 meters. But really, all they need is a camera that's pressure rated to 300 meters and has a black and white CCD, but is super sensitive because they are going to use it in low light conditions at night or at a depth where light's not penetrating to. So again, making sure you understand what the client wants, and then correctly interpreting what they're asking for into a design is key here. And setting that up early, making sure you know those needs and requirements first, not necessarily just what they're stating you, but try and get the full context, the full scope of the problem they're wanting you to solve. Again, the next thing would be starting with a predetermined solution and making the problem fit. I did cover that before, but it is often a stumbling block, let's call it that, because it kind of gets you on a one-track mind, and a lot of the time there could be another solution that's more effective or more efficient, whether that be time or cost effective. It could be both, but just try not to, the first idea you come up with, use it. Again, start at the problem, work backwards from there. What's the minimum thing that would meet criteria that the client has set? Plan for resources. So this one's difficult, I think, at any stage in your career, is correctly estimating the resources required for a design or to complete it, and that could be just to do the design or actually bring it through all the way to fabrication. Things always come up, things you never thought about before, things the client never thought about before. Scopes usually do change a little bit in the process of larger designs. So what really helps here with planning resources, again, is that initial scoping document and getting everything down on paper and making sure it's down on paper in a logical, cohesive way that's easy to understand, and then you can come up with good resource estimates from that. Documentation, because basically none of the things that I just mentioned would be possible without the documentation. But again, documenting every step of your design process and make sure it's somewhere where it's easily accessible and easily recovered from, if you know what I mean. So a lot of the times you'll be working on it in industry, you'll be working on a design, you might get pulled away to work on something else that's of a more urgent nature. Going back to the design that you're working on is a little bit of a headache, just because you're not fresh. Everything is not fresh in your mind with the design. So having the proper documentation and good documentation in place helps you jump back into that design quicker, and it increases your efficiency, and also I would say the quality of the design in the end. Further, sometimes documentation is required for design. So whether it be for a standard or by the client, you're going to have to document your design process, or your testing process, etc. Dealing with non-technical clients and technical clients as well. So you can kind of get two types of clients, and non-technical clients is often just the translation between technical lingo and what they're trying to tell you. So they might not know engineering design, how it operates, the process, or they might know it very well, but there are two kind of different problems there, really come down to the same thing, and it's communication and understanding the needs of your client. So while a non-technical client might have no idea, not be able to state the problem correctly initially until you dig a little deeper, the technical client might just try and make the leap and say, hey, here's the solution that we want, like I said about the camera system. But they don't know about your side, your specialty, or your expertise in this area, and they might be overcomplicating the situation or overcomplicating the solution in this case. So again, communication with the client is key, and make sure that you really get the context of what you're doing. And then, what other ways do clients affect designs? Well, most of this has been covered earlier in the talk, but just to highlight them again, clients are really involved in defining the problem and setting the scope of the problem. So again, that also includes the constraints, and a lot of the time that's non-engineering, again, non-engineering constraints like cost and schedule. Clients are also often involved in formal design reviews. So I didn't go through here in the design cycle, but when you move to a commercial environment, you're probably going to have, again, as part of your documentation requirements and your design process, some kind of formal review. You can look up the engineering design, US government, I think, formal design review process on Wikipedia. There's a big Wikipedia article there with all the stages and the types of the reviews that go through. But essentially, you'll end up with a couple of reviews that start with after your first prototype is kind of chosen and you start progressing the idea, and you'll document that, and then you'll do a critical design review where you have a pretty fleshed out design and you're going to really go through that design with all of the disciplines that are involved in the design and look at it in critical detail, and then that will get documented. And then after all of those concerns have been included in the design, you'll probably go into something like a production review. So is it ready for us to actually build this part, or is it ready to send out for somebody else to build this part? And then after that, it would be a test review. So if you do a test of your product to make sure it's a quality test after it's produced, to make sure it's okay to send to your customer, then you'll probably do a readiness review for that and document it. So a bunch of documentation standards play in here, and ISO 9001 is probably the most commonly or most widely recognized. And that is just about traceability of design and traceability of materials and parts and everything as well. But since we're talking about design, all of this record helps you trace back the decisions made in the design from initial concept generation down to the part actually going out somewhere. So if in the future you need to change anything or need to know why design is made or a decision was made, you can actually go back and trace it. And just a couple of tips for dealing with clients and how to be, I'll call it successful, but it's just good all around, I guess. Again, highlighting the solution the client needs might not be the one they initially identify. So make sure you try and get as much scope as possible. Don't just say on the face, yep, cool, got it, done, and go and create a design. Really make sure there's nothing else that you're missing or that they're forgetting about. Stay in constant contact with them throughout the design. That helps as well. Communicate in non-technical terms with non-technical clients. As engineers, we do tend to just slip into technical jargon. I was actually emailing with a friend who's a marine biologist just the other day and mentioned something about manufacturing. And she said, nope, don't know. So we kind of forget. For us, everything that's common, day-to-day usage, day-to-day language isn't really that common outside of engineering a lot of the time. So make sure you're aware of that, and where possible, communicate in non-technical terms or make things understandable for a wider audience. And the final thing would be manage expectations. 3D printing is another one of these, because if you talk to people who don't use it much or aren't involved, they are under the impression that you press a button and then a car comes out the other end of the printer. That's not really managing expectations. So make sure your client is aware of what they're getting, what the solution will do, what the solution won't do. Again, that comes back to scoping it out well. And then stay in constant contact with budget and time constraints. If you think it's going to be delivered late, the earlier the client knows that, the better. In my experience, they would definitely prefer to adjust their schedule than to tell the people that they're working for that everything's great, and then a day before find out it's going to be delayed by another 3 days, because then they have to go and update the client. So it's a waterfall effect there. Getting that notice in advance actually usually helps the client plan better, and sure, they still have to move the date, but then they can move other things around to make it work. So again, manage the expectations about what they're getting, the quality of what they're getting, the cost of what they're getting, and also schedule. So I know everybody's dying to know what happened to Splat and consulting engineer Kitten. Well, Splat ended up with a solution to his problem, and he was so happy with Kitten's work, he poached her from her employer and brought her onto his team full time. And I think that is a pretty happy ending to the story. So if anybody's got any questions or you just want to chat about design or anything related, I'm free for the next couple of minutes here. Kyle, I guess you can take over from here and get the Q&A.
Perfect. Thanks a million, Greg. Great presentation. Just wanted to highlight, really liked that point you made on context in your presentation there. A lot of people try to walk away from designing things with a part of the picture, and the more time you spend understanding your constraints and what they mean, the more informed you can make your designs. So I really like that you highlighted that, along with documentation, which is something a lot of people don't understand the importance of until you're looking at a 20-year-old system and you're trying to figure out how it was put together.
Yeah, absolutely. And it's also something that you kind of do it in your academic career, but subconsciously and probably not in the manner you should. And once you get into the commercial environment, you're like, I don't have to do that anymore. I just design stuff and get paid now. It's not really true, because you probably won't be with whatever company you're working with forever. And just to your point, I've had some work terms where I worked, and one of my very early ones actually was updating some P&ID drawings, and you would go out into a process area and just look at the drawing, and that part of the plant didn't even exist anymore. So
Yeah,
it's a bit of a headache there when documentation is not kept up properly and it's not maintained properly or not done properly in the first place. So don't just think
absolutely.
about you, think about all the people coming after you and touching your design.
Absolutely. All right, so everybody, I'm going to be monitoring the chat box here. So anybody who has questions, feel free to post them in there. And if you want to ask Greg your question yourself, or as he mentioned, hop in for a chat towards the end, just let us know and we'll promote you to panelists so you can be part of the discussion. So our first question is from Iman. So he says, I find the idea of making the problem fit a predetermined solution a little confusing. Shouldn't we be starting with the problem? So Greg, would you mind elaborating a little bit more on what you meant by making your problem fit your solution?
Shouldn't you be, and what was the rest of that? Shouldn't you be starting with the problem?
Yes.
Yes, exactly. That was my point. What I was saying was that a lot of people actually have, some favored solution that is overkill. It's more than you need for a problem, or it doesn't really solve it that well, but you want to make it work anyway. So if you don't have a good scope set out for your problem, you're just going to favor this solution, implement it, and then either it's going to be more expensive than it has to be, more complex than it has to be. It might actually not work. But a lot of people, and again, 3D printing is the perfect example there. Everybody wants to bring in 3D printing to their manufacturing location and just 3D print everything, but it's actually not that good, and it's not cost effective for a lot of things. So that's what I mean when people get hyped up about a solution and then they go looking for places to implement it and stick it in. So this isn't necessarily actually just involved in clients and design for clients. It could be internal processes. It could be just in things that you do in everyday life. Make sure you're starting with the problem and working backwards. Did that clarify that a little bit?
Iman, just ping us if you wanted to elaborate a little bit more. So while we're waiting for Iman to respond there, the next question is from Manib. His question is, for documentation, should it be a group task or should one person be responsible for an entire document? For example, one author for a piece of writing or multiple authors?
No, see, that's one of the context things. And one thing you'll notice when you go out into the workplace from your academic career is that really things are a judgment call. So I can say yes or no, but there's actually no clear cut and dried answer there. Sometimes it's better for one person to do the document. Sometimes it's not even possible for one person to do the document because of the scope of the problem that you're working on, and it might include disciplines outside your specialty. So usually you'll have one person who's responsible for the document, and that will just be making sure everybody contributes their parts, making sure it's reviewed by everybody, and then that would be compiled into an overall cohesive document, but parts of that document are written individually. And I think the larger your design gets, the more that has to happen rather than one person writing it, because I'm not going to write the electrical spec for anything. At a high level, very high level, maybe it needs electricity. But once you dig past that, that's going to have to be done by an electrical engineer. If we're both working on the same design, if it's Kraken, they're working on something for sonar electronics, I'm working on the thing that keeps the electronics from getting wet. We're going to have to talk to each other, and we're working on a scope document for that or a design document for that. We're going to have to contribute our individual parts. Somebody's going to have to be responsible to make sure electrical, mechanical, and everybody else required contributes their parts appropriately and reviews it to make sure everything fits together and the information is correct. But it's not going to be done by one person as a whole.
Perfect. Great answer. Thanks, Greg. Next question is from Solange. And They ask, I'm not very clear on what a scope is. Could you please give us some more examples?
Scope would be a definition of what you are working on. So I guess literally it's you're putting blinders on a problem. So by scoping a problem, you're saying, I'm going to solve this specific thing. That's called the scope. What you're working on, what you're actively trying to solve, what you're looking into, what you're looking at, what you're examining is your scope. Everything outside of the scope, you're not really trying to solve. It might affect what you're trying to solve, but you're not trying to solve those problems. So your scope is the things you're actively dealing in, looking at, looking into, trying to solve. Does that make sense?
Okay, thank you. That helps from Solange. So while I wait for more questions to ping into the chat, I had a couple. So Greg, what do you think is the best part of being a designer at a tech company?
You know, and now even I'm probably out of the weeds a little bit and more managing design at a bit higher level, but I really, really, really enjoyed being in detailed design because it's very rewarding. And it's different for everybody, you know, but I really enjoyed solving problems. I loved having a solution that I'm getting asked to solve because a bunch of people couldn't come up with something. I'm like, hey, I feel smart because I came up with something that solved this problem. But it's a very rewarding, you know, just environment to work in. And when something works, it's a pretty good feeling. It's not a great feeling when things don't work. And I have some stories that I'm not going to tell in a recorded presentation. But if you're ever talking to me, you can ask. Because, you know, failure as an engineer is a thing. It's going to happen. So don't just get discouraged when it does. And the downsides usually, you know, are far outweighed by the upsides. So for me, again, you know, the reward and also, and it's interesting. I'm kind of delving outside of engineering now, but there's a concept called flow, and I'm a mountain biker, so flow in mountain biking would be when you're riding down a crazy technical hill, just fast enough to feel like you might die, but not quite fast enough to actually do it. So you're at the very peak of your skill level, and you're accomplishing as much as you can. You actually have a mental state change, and it's known as flow in athletics. So that actually applies to other areas of life too. And you know, you could say that if you're working on a design that is challenging you to your utmost, but it's actually not too hard for you or not too easy, you enter that flow state, and it's just a kind of a state of euphoria. I mean, you know, relatively here, but it's a great feeling, and time flies by, and you just feel really good when it's finished.
Okay, great. Next question is from Jeremy. Regarding time constraints, does sourcing for prototype parts and materials cost a lot of time?
The sourcing for prototype parts and materials
Cost a lot of time, or I guess take a lot of time.
Yeah, you know, procurement is often a very time-consuming thing, and again, this is completely dependent. If I need a couple of nuts and bolts, I get them from McMaster, and they're here in 2 days, usually tomorrow. So stuff like that doesn't really cost a lot of time. But if you're asking for a machine part, you know, things are going to lead into how busy is the shop, is the material readily available, and working in Newfoundland, not to mention COVID, but just working in Newfoundland, at the best of times, we do have a limited amount of material available locally. So we have good stock of the things we use all the time. But for instance, if you want 6061 T6 sheet, you're probably not going, that's aluminum sheet for anybody who's probably not mechanical. That's probably not going to be a great stock of that locally because we tend to stock 5032 or 5052, 5053 here for boat building. So depending on what you want, yes, but sometimes no. Again, it can really vary depending on what you're looking for and the availability. And again, moving into winter is another thing in Newfoundland. You have storm delays, weather delays, so you can sometimes tack a week onto parts showing up that you've ordered.
Yeah. So, Jeremy, to build on that, a recommendation from me would be in any part of your design, have a look at the things you're going to need to procure well in advance, and then make sure that if if you have to plan for a 6 week lead time, you identify that, you know, early in your process so that you're not stuck, 2 weeks away from a deadline and you need something that needs to be there that can only get there in 6 weeks.
Yep.
So it's important when, in any part of engineering to make sure that you're looking at the logistics of how you're going to implement.
And just to highlight, which I brought up a little earlier, sometimes, that lead time not working for you makes you kind of fit a square peg in a round hole, and you have to work with something that is available in the time frame that you need. But again, there's always mitigation factors for all of this, and like Kyle said, scoping out your lead times early, as soon as you identify the parts that you would need, can help there.
All right. So the next
items.
Sorry, Greg.
Oh no, just long lead items.
So the next question is from Laughter. What prototyping software would you say makes you the best prepared for specialist jobs in engineering design if you have a background in mechanical engineering?
Prototyping software. It depends on the region that you're working in. If you're around here, Atlantic Canada, here mostly, it's almost always SolidWorks. You might see some Inventor, possibly if you're working for one of the offshore oil and gas companies, some AutoCAD there. But for tech, mech, locally, it's probably going to be SolidWorks. After that, it really depends. You're getting into such a specialized area that it's probably not that common. Yeah. Past that, I wouldn't actually really say. And it's not prototyping software. It's CAD and CAD analysis software. If you choose to use that for a prototype, great. I don't know of any specific prototyping software that I would really recommend getting to learn or anything like that.
Yeah. And there's a lot of different CAD softwares out there. When I worked in the US, NX was very popular. Navisworks was very popular. Fusion 360 was very popular from a CAD perspective. But it seems that ANSYS is probably the standard for a lot of analysis. So getting familiar with ANSYS might be a good place to start if you're looking for specific softwares.
Yeah, and I call that analysis software, not necessarily prototyping.
Yeah, exactly.
And then it's actually, because ANSYS is quite expensive, you can get a free student version for the whole workbench. And it just has a limited problem size. But another thing you're seeing now, if we're talking about fluids, is probably going to be slipped my mind. I'll see if I can find that.
But on the topic of ANSYS, the Student Design Hub is going to have full licenses available in the lab when we open up in the fall.
Perfect.
So
that's awesome.
If anybody wants to come in and do any heavy analysis work, we'll have a couple workstations that are decked out for that.
And I'm pretty sure Cornell University has a course that kind of takes you through a bunch, and they have a sim cafe available online that will take you through a bunch of ANSYS solutions. Yeah, they're great.
Excellent. Next question is from Solange again, and they ask, what mechanical engineering stream did you complete, Greg?
So a lot of the streams that exist now didn't when I did. I did thermal fluids, which is kind of weird because I after graduating, I mostly work in materials and structure. So, but yeah, thermal fluids, and I guess mechanical equipment, but optimization. But I did thermal fluids.
Yeah, the mechanical focus streams only came in, I feel it's like 2015 or so, somewhere around there. Prior to that, I think it was just core mechanical and oil and gas.
It was, yeah. But then you did have, I guess it was the last two terms, you could choose your courses, and depending on what you choose, you would. So I chose thermal fluid and mechanical equipment optimization courses, and that would basically be your thermal stream now.
So a follow-up question from Solange. Which of them best prepares you to enter design in the field? So I guess Solange is looking for a little bit of guidance to move into the field of mechanical design.
It's hard because there's so many aspects of mechanical design, And again, like I said, I did thermal fluids in school, but once I started working, I did optical design for a little bit, subsea, delved into that, and some systems there, and then really got into more materials and structure and welding. So, I would recommend the courses that, and I don't know what courses are available to you right now, or all of the streams that are available. I think the most common one that would be applicable if you have a materials or solids stream. Corrosion is another fairly popular one, but it's pretty specific. But I would say kind of some of the courses that lead up to your specific corrosion courses would be very useful industry. But then again, there's probably a couple of jobs out there that require an in-depth knowledge of fluids and fluid analysis. So really, I think you'd have to go a little bit, target your focus a little bit more if you take some of these more specific courses or streams. But that's not to say it doesn't prepare you well. It's just preparing you for a slightly different market segment. So what market segment do you want to work in? Figure that out, and then pick your streams to suit. All of that being said, it's called practicing engineering because you practice it. So when you graduate, you're still not really that prepared for design. So, 90% of what you know will come in the workplace. And sure, you'll reference what you learned in school occasionally or on a daily basis, depending on what you learn. But the main thing is you came out with an engineering degree and you can solve problems. So it's easier for you to learn from somebody who has experience, who's a senior engineer, who has that knowledge to how to apply your knowledge to a specific problem. And that's the practicing part. So the real advice is practice design as much as you can. You don't get a piece of paper for it, but that will make you a better designer.
And I'm going to take the opportunity to plug our student design teams. A great opportunity and a great way to get more involved with design while you're a student is to get involved in one of the groups we have here. Depending on what your interests are, there's groups like the Baja team, Eastern Edge Robotics, Paradigm Hyperloop, a couple of new groups that have formed. We have F110th, which is the autonomous race car group.
Cool.
We have the RoboSub team, which I think Mordecai is still on the call. And there's plenty of other ways to get involved in design and do some really cool stuff while you're a student. So I'd encourage anybody on the call who's interested in getting involved, reach out to me, and I'll ping my email in the chat there, kdoody@mon.ca, and I can give you a list of all the different groups that I know of that are, you can get involved with, and hopefully I can get you hooked up with the right people to start making cool stuff.
I'll put a plug in for that as well, Kyle, actually, because if I'm going through resumes for a student application on a position, whether it be at Kraken or anywhere else I've worked, I'm actually looking for your design experience. The first thing I'll look for is, are you on Munbaha? Are you on a team where you actually practice design at one? Your courses are kind of secondary to that. I want to see if you can apply the knowledge that you have from school to a real world situation. So that to me is probably a very valuable use of your time, getting involved in those teams, getting involved in the design of things.
So while we're waiting we've got a few more minutes, so while we're waiting for some more questions to trickle in, one question I always like to ask, Greg, is what are some good practices to keep in mind when you're designing for manufacturability?
Oh, put me on the spot here.
That's a tough one, but I always get great answers. So,
and again, you can curse 3D printing for this as well, but because 3D printing isn't the solution for everything, I think one of the difficult things for junior engineers is actually to understand that you have to make your design. Sure, you can click it and put it up on screen, and you can probably 3D print it. But if that's not the process you're using, then somebody else has to make it for you. And there are things that can't be made using conventional techniques. So gaining a better understanding of those techniques most of the machine shops here, if you work with them on a regular basis, so if you work with a company or you go into the workplace, you're working with a company and you have a machine shop that you're working with, ask them to go down and like take you through their equipment and look at how it works. YouTube's there, of course, so you can always figure those things out. But the key thing there would be you have to get familiar with the production method in order to be able to think about how something's going to be produced during the design. So if you're not familiar with 2.5, 3, 4, 5, 6 axis machining, it doesn't really matter what you're thinking about during the design phase because you're not really going to interpret how this part is going to be made correctly. So again, practicing engineering, the more you do it, the better you get at it. And another thing I'd suggest there is really stay in contact with your machine shops. Become friends with your machine shops. They keep messing stuff all the time, and you have to send it back a lot of the time. But they're there to help you, and you're there to help them, and they'll do it in any way possible. So look for suggestions on how to make things easier to create. Or if something comes in out of tolerance, ask them why. Say, hey, was this just a miss on the machining, or is there a way I can make this better, or is there a way I can draw this better and describe it better so that it gets machined better in the end? So designing for manufacturability, on its face, what you're trying to do is consider how something's going to be made when you start your design and lay it out in the same way. So for instance, let's take 3D printing because it's an easy one that probably everybody uses. If you're using an FDM machine and a single extruder, you're probably going to try and design a part without any overhangs or without any 45 plus degree overhangs, because if you use support material, you're going to have scarring on certain faces, or you're going to try and design it in such a way that the faces are scarred are ones that you don't need to be flat finished or perfect anyway. So again, what you're doing there is considering the outcome of the part when you start the design. And the more familiar you are with the production method, the better it is. So get experience, get familiar with production methods and how things are manufactured.
And for any folks out there who are interested in that, we do have a machinist here on staff at the faculty. So you can come down to the machine shop anytime, and Jason is there every day of the week. So if you have questions about manufacturing and does the part that I've come up with make sense, how would I make it? He can certainly, if I'm not available, he can certainly advise on that. And in a lot of cases, he'd be absolutely happy to walk you through making it yourself. So I would just say, if you have time in your afternoons or you're between classes, come on down and make something. And the more hands-on you get with things, the easier it's going to be for you to get better at designing for how you're going to actually implement your solutions down the road.
And yeah, just to highlight what you said there, Kyle, I really think that building your own designs is key for a junior engineer or junior designer. Get out there, put things together that you made in CAD land and see if they actually work in the real world, because you're going to be able to discover your mistakes a little bit sooner. And you know what? You're going to remember them a whole lot better. So the next time you're making something, you'll be like, right, I couldn't get that board in the bottle last time because of this. And you're not going to make that mistake again.
Absolutely. All right. Well, that looks like that's all we have for questions. Greg, thanks so much for taking the time to do this talk today. I think we had a lot of great discussion, and I think a lot of the students really enjoyed chatting with you. Guys, before you disengage from the meeting, there's going to be, when you click exit, there's going to be a survey that pops up. It's totally optional, and it is 100% anonymous. It's for giving us feedback on how we can do better. So if you have some feedback on what you'd like to see for the next speaker series coming up in the fall, feel free to give us some context. Thank you all very much, and have a great day.
Awesome. Thanks, everyone.